Hi, my name is Shamir. I'm from Google Pittsburgh, and I'm going to talk about logistic regression, regret. And I also would like to thank Matt Streeter, whose helpful discussion throughout the process of this work were very pertinent to this work. So logistic regression is the tool of choice in many machine learning problems and in many realistic systems. But we still don't quite understand its regret behavior, or at least we don't have very tight bounds either to the rate or the constant of regret. So in this work, we're making a connection between logistic regression regret and machine learning regret in general, and a lot of established results in information theory when we have redundancy or regret bounds for different settings and different classes. So we're specifically interested in the online learning, where we play in rounds. At round t, out of capital T rounds, we observe a feature vector x of dimensionality d, and we restrict the feature vector by L infinity, and we need to predict a label y of that for that feature. We also use the notation of the sequence of past up to t example label pairs as S of t. And the role of the algorithm is to generate this prediction, and it incurs a loss at each example, and it incurs a cumulative loss over all the examples. Specifically for logistic regression, we have positive and negative labels, where the prediction is the sigmoid of the dot product between the feature value and the parameters we learn. And the loss is just the negative logarithm of the prediction. And specifically, for an algorithm that generates this prediction, it incurs a loss, which is the negative logarithm of its prediction. The tool of choice in many systems is stochastic gradient descent, where we update the parameters by taking a step against the gradient of the loss, where the step is a function of either time or specifically of the coordinate in other grad or any other schedule we can think of. A more generalized setup is that of the follow the regularized leader, FTRL, where the parameters are updated to the parameters that minimize the cumulative loss with some additional cumulative regularization that is added to the loss. And the loss could be the true loss or could be a surrogate loss. And there are many papers that use FTRL setup, and SGD can be framed as a special case of FTRL. The other framework that addresses this problem is that of Bayesian methods, using a Bayesian mixture or model averaging, where we basically assume a prior on the parameter, and the prediction is an average or a marginalization over this prior of the probability of the label. Specifically, we can view this as we assume a prior at the beginning of time. In every round, we average the prediction over the prior, and we update the prior to a posterior, which becomes the prior of the next round. And the posterior can be viewed as the joint probability we assign to the parameter and the label, normalized by the marginalized probability of the label, marginalizing out the parameter. So we define regret as a benchmark of how good our algorithm is in the online setting. And you usually define it relative to some constrained comparator space, theta, big theta, where the constraint is constrained by some ball B usually, where the ball can be taken in L1, L2, or an infinity. And we usually compare our algorithm to the performance of a point theta star in this space. So the regret is defined as a loss, the cumulative loss our algorithm incurred over all rounds, minus the cumulative loss an algorithm that consistently played theta star incurred. And we can think of a best comparator in the class of comparators as the one for which that loss is minimal, and the regret can be defined relative to this best theta star in the class theta. So regret and redundancy in information theory are the same thing when we talk about online learning. And there are a lot of results in the information theory literature about redundancy rates. Specifically, there is the multi-M label problem, where we're still in a single-dimensional logistic regression problem, D equals 1, but we have multiple labels. And for that problem, in information theory setting, there are many results that show that the regret consists of half log t over m per each parameter we need to learn. Or there are m parameters. There are half log t over m cost for each of them. This was derived initially for fixed n in results like Davison, Khrushchevsky, Trofimov, and more. There are later results that actually show that this is generalizable to any m as long as m is sublinear in T. There have been a lot of work in the convex optimization for regret bounds. So if we think about strongly convex loss functions, then the regret has been shown to be logarithmic in T and linear in the dimension. In the weakly convex setup, it was square root of T and not logarithmic. And there is a lot of work of general minimax bound by Racklin recently, deriving all sorts of bounds to more general problems. Now, logistic regression specifically is considered a weakly convex loss. However, there's been work by Bach that showed in a series of papers that it's actually weakly convex, but locally strongly convex. And depending on the Hessian eigenvalues, we can, in some cases, achieve logarithmic regret in T and linear in D, but not always. And if the Hessian is misbehaved, then we do not achieve these rates. Now, going back to single dimensions, in information theory, we've seen that for a single dimension with single parameter, we pay half log T redundancy or regret for this parameter. Now, if we frame it as a Bayesian setup, we use a Jeffreys prior, which happens to be the Dirichlet 1/2 prior, we basically get the Khrushchevsky-Trofimov estimator, which guarantees half log T redundancy or regret. What's interesting, though, is in McMahon and Streeter in 2012 have shown that you can frame the Dirichlet 1/2 prior into an FTRL problem and also get the same similar regret bounds. But instead of using a Bayesian approach, you're using a more like gradient method approach, and you achieve the same regret bounds. However, McMahon and Streeter posed the question of whether this generalizes beyond a single dimension, because in this case, in a single dimension, all these methods seem to be equal, but unfortunately, the results do not generalize beyond d equals 1. The first paper about that created a little more confusion is actually Hazan's result that actually shows that if the algorithm plays the theta prior to observing the example, even in a single dimension, it is guaranteed regret of t to the third, which is over logarithmic. And when the dimension grows larger, a regret of square root of t is guaranteed. Point is that Hazan's results fall in a proper setting, which is a setting where the algorithm is not allowed to observe x before playing theta, which is more difficult to the algorithm, and therefore the algorithm results in larger regrets. The algorithm suffers larger regrets. In the improper setting, on the other hand, the algorithm is allowed to observe the example before actually making a prediction. And by that, it actually allows doing a full Bayesian mixture, as we described before. So the first result, to the best of our knowledge, into that was by Kakade and Ench, where they use a Bayesian setup with normal prior and normal variational distribution as a tool to derive the bound with some variance in squared. And they were able to express the regret for this problem as a logarithmic term on the right, plus a penalty that is a penalty of the prior that they choose on the comparator. Unfortunately, if we don't go farther from this expression, you could have a situation where the left term overwhelms the right term and the regret becomes higher. Foster recently showed that these mixture approaches can actually be used to derive with a uniform prior to derive a logarithmic regret in T linear in the dimension upper bound, but still with constants that are higher than the lower bound with the bounds we expect. And also in a very specific binary features case, a linear regret bound on a number of dimensions. So what are we doing in this work? In this work, what we want to do is to leverage techniques that are very successful in the information theory community to derive regret lower bounds. Specifically, we want to leverage the redundancy capacity theorem, and a weaker version than the strongest that there is sufficient to our needs here. And the theorem is basically the following. If we take the class theta of comparator values, and we let the horizon go to infinity, and if we're able to choose m points on this class that are distinguishable, meaning that we observe the label sequence generated by one of these m points, and with probability that goes to 0, we decide that it's another point, then if we have this distinguishability, then we can show that for the worst case, the worst comparator case, or the worst sequence, we can lower bound our regret by log of the number of distinguishable sources. So this gives us a recipe to actually compute lower bounds on the regret. We take a grid of points, and we have two things to prove about this grid. One is count the points in a grid, and the other is prove distinguishability in the grid. If we do both, we can use this theorem and derive, and the log of m becomes a lower bound on the regret. Going back to Kakade and Eng's work, we can extend on this work to derive upper bounds using variational methods. The general idea is come up with a prior P0 and a variational distribution Q whose mean matches our comparator and whose variance is upper bounded. Both prior and variational distribution have a diagonal covariance, and then we can show that the regret is upper bounded by the divergence, the KL divergence between the variational distribution and prior, plus a term that is linearly dependent on this upper bound on the variance, T and D. And in addition to what was done in Kakade and Eng's paper, we can actually make this happen also for discrete distribution. We don't have to have the distribution as continuous. But we can use this tool to prove the upper bounds. So using both methodologies, we basically can show that the regret for smaller dimensions is logarithmic in T and linear in D. And depending on the size of the ball or on the norm which we use to constrain our comparator space, there is a correction factor in the logarithm, which is a polynomial in the dimensions, depending and higher for the lower spheres or lower balls we constrain on. And the bounds differ as we increase the sphere, the bounds differ by this parameter, and we also have a difference between the upper and lower bound in one scale of D. Now, these bounds go up to larger D, but at some point, because of the normalization by the polynomial term of D, we basically get stuck. So we can come up with lower bounds that actually are sublinear and in T, and also upper bounds that get rid of the logarithmic term in T. And specifically for L1, we see that we can get regret bounds that are small o of D. That means we get regret smaller than the sublinear in the dimension, and we don't have the logarithmic factor in the L2 case. On the negative side, we have guarantees in the L infinity case that as D grows larger than square root of T, we are guaranteed to have regret that is O of D log of T, and we cannot go below that. So to prove these lower bounds, to prove both the lower bounds, we use the redundancy capacity theorem, but we simplify the problem. Partition the sequence into these segments where each parameter lives in one segment. The richness of the segment contributes to the grid is square root of T over D distinguishable points that are spaced by square root of D over T. We add an epsilon to guarantee to the exponent to guarantee distinguishability. We count and we get the L infinity bound. We normalize by the volumes to get the L1 and the L2 bounds to give the other regions. And bounding by the maximum value for D, lower bounding by that on the smaller D than when the bound becomes useless, we give the upper regions. For the upper bounds, we use Kakade and Eng for L2 and L infinity, but we just go farther by minimizing over me, and we come up with a variance that is very large, but actually gives the logarithmic regret. For L1, we do a discrete version of this. When we generate a Bernoulli variational around theta star, we mean with a side epsilon on the discrete grid that we take, we minimize over the dimension, over the epsilon, and we come up with the upper bounds. For the extreme cases, we maximize over the dimension. So to conclude, we characterize the regret for logistic regression on all regions. For small d, and we saw logarithmic in T behavior, linear in D. We also characterize the asymptotic behavior. We adapted the redundancy capacity theorem from this problem. We showed that we get, for L2, we can get regret rates that are no longer logarithmic in T, and for small d L1, we basically are sublinear in D. On the negative side, we are guaranteed to be square root of T or larger for larger D for L infinity, and we cannot do better than this. Thank you very much.